This is a demo of Adaptive Computing's HPC Cloud On-Demand Data Center, or ODDC product, using the Extreme Scale Scientific Software Stack, or E4S Pro image on Oracle Cloud Infrastructure platform. ODDC gives you a web-based interface to manage a cluster and all aspects of a cluster management on a system such as OCI. It helps you in configuring a cluster, building a software stack, monitoring jobs, a file manager, deploying a cluster, accounting, even looking at the instance prices, so you can see how much an instance costs in which region of the world. And then you can even have a dashboard that connects to the head node. You can launch a cluster. Now, this is a cluster running on Oracle Cloud Infrastructure. I can see that there's a head node, and there are 2 compute nodes over here. And I can go to the configuration, and I can click and open VNC viewer. When I click this and authenticate, it brings up a desktop view like this. Now in this, I can set up my system and connect to this through a remote desktop environment. With this, I can launch the jobs. I can have a head node. Here is, say, a terminal application. Let me just bring this up. And I can then use this to evaluate the applications, run my jobs, and it gives me a graphical interface. Let me just change the size of this font so it's easier to read. Let's go up to, say, 18 and see how that looks. Okay. Now, E4S, the extreme scale scientific software stack that forms the basis of software deployment on this image, is built using the Spack package manager. And it includes many different AI and HPC tools. There are over 100 different packages such as Tau, Trilinos, Visit, and they are available to you using the Spack package manager. Here is a demo of Visit. And I can say Visit and launch it. You can see the GUI come up. And this remote desktop environment based on VNC is very responsive. I can open up examples.silo, add say a pseudo color or pressure, and draw it. And here is the 3D view. If I add an operator, for instance, slicing operator, isosurface, and draw it again, I can see this view. There are other visualization tools, including ParaView. We have the ParaProf profile browser. I can look at previously created PPK file from Tau. Tau is a profiling and tracing toolkit. Let me just go and change the preferences, increase the font size, and make it bold, increase the font size, apply it, and then cancel. So I can see how much time is spent in which loop, in which function. And let me not stack the bars together. And I can, instead of seeing all the MPI ranks in this way, I can just look at a 3D visualization of this. And here, I can see the triangle mesh, a bar plot, which shows me an MPI rank display, which shows 0 to 255 ranks, the functions over here, and the loops. And also, I can see the time spent, the exclusive time spent or hardware performance counter data along the height and the color axis. Here, I can even go down to a specific function and see what's going on with the crosshairs. So here, for instance, I see that on rank 206, it takes 8.4 seconds. If I go down to 199, I can then see over here that there is this rank 199, which is taking about 129.5 seconds. Now, this is a simulation of a tokamak reactor, a cylinder, and the CPU that gets the central axis has to do more work. So you can see that one CPU is taking a lot longer. I can look at scatter plots, which show me the time spent in different functions from 31 seconds to 260 seconds in MPI barrier. And 4 such functions are chosen based on their standard deviation. And I can see each rank has a unique value for these 3 functions and the color function. So these 2 functions are inversely correlated to each other, the MPI barrier and sigma d CQL3D, and all these ranks form a -1 correlation coefficient line. And there's one CPU, the red hot CPU, that's doing something different from everyone else, which is over here. So these are the 2 functions that are inverse of each other. And half the machine is doing this, the other half is doing this. So you can see artifacts in this 3D view. And of course, you can look at the performance data in detail. So this is just one application. Let us look at some AI ML applications that are bundled with E4S. So let me go to TensorFlow. TensorFlow is a framework that makes it easy for you to build and deploy machine learning models. Here is a run.sh script, and I'm just going to look at this f3.py. You can see we are importing Keras from TensorFlow. There is a stage for training. And let me just run this, where TensorFlow will be bundled as part of this image. There are other frameworks that are part of this E4S distribution as well. So here we can see it running on OCI. And here we go. Let's go to PyTorch. PyTorch is a fully featured framework for building deep learning models based on the Torch library. It's used for applications such as computer vision and natural language processing. And here is run.sh. I'm just running the Python code. Let's look at this f4.py. And here is the import torch statement where it's running this on the CPU. And this is to just show that the library is correctly installed and it can run this code. Now, JAX is another framework. And JAX is a high-level, high-performance numerical computational library that is built on top of NumPy, and it offers a number of advantages over TensorFlow, including speed. JAX is significantly faster than TensorFlow for many tasks. So here is run.sh, and I can just say run.sh and launch this. There are other frameworks that are also included in this, and Horovod is another application. Now, you may want to use all of these Python packages for AI/ML tasks and use them through an interface like Jupyter notebooks. And Jupyter is available as well. Many GUI tools, including those running in a web browser, are available because you have a remote desktop environment. With a full desktop, you can launch all these jobs, you can access the compute nodes, you can then run your applications. What is interesting about this E4S framework is that it's customizable and it's extensible. So if there are packages that are not installed over here, because every user's needs are different, you can install those very easily. Let me give you an example. Let's say I have a Python interpreter, and let's say I want to import TensorFlow. You'll see that this is available to us, and I can import PyTorch. I can import JAX, I can import Keras, can import Horovod based on MPI. Then a number of other packages that Python developers use. Pandas. What else is there? Say NumPy, import SciPy, import Matplotlib. And you get the idea. There are a number of packages that are pre-installed. Now, what about those that are not installed in this distribution? Suppose I wanted to use, say, OpenCV. Oh, well, OpenCV is installed here. How about scikit-learn, sklearn? Now, sklearn is not installed. Now, how does a user handle that? They can simply say pip install -- user scikit-learn. And then you can install this in the home directory, and you will have this available to you. So next time you try Python and say import sklearn, it's there, along with the other tools such as Pandas. The same thing goes for HPC tools. You see, we have Spack package manager, and if I say Spack find -x, it shows you the high level over 100 different packages that are installed here. Packages like HDF5, OpenMPI, MVAPICH, MFEM, Tau, PAPI, a number of different tools. Now, if there is a tool that is not installed here, because these tools, if I want to say, show me where is MFEM, I could say Spack location -I MFEM, and it will show me where it is installed. Now, there are two versions of MFEM. I can say Spack location -I and pick this one / with the hash, and it will show me where it is installed. Now, this is installed in the Spack directory, which is a read-only directory. If I wanted to install another tool, let me see if I have Valgrind. I don't have Valgrind, so I could say Spack find Valgrind to see if Spack has this Valgrind. It does not. Spack info Valgrind, it shows me that it is there. So I could say Spack install Valgrind. And then it will install it in the home directory, which is mounted on the compute nodes. So if I were to go on to another node after this installation is done, it will have that package installed from it. So this is the way we can look at a package installer and expand on what we already have. Now, let me just open up another terminal window, and let's go and see if we can use these Python-based tools in a Jupyter notebook. So if I say Jupyter notebook and cat this matplotlib.txt, okay, let me just copy this and say Jupyter notebook and launch it. So it will launch the web browser, and it will connect to that. And let's open up a new Jupyter notebook. So I'll say new and notebook. And because we have a remote desktop, a a web-based interface is easy. I'm clicking here and then saying Shift Enter to run this cell, and it will use the matplotlib package to plot this graph. So you can see the graphics packages all work seamlessly within the Jupyter Notebook environment. And I can close it over here. Here it is trying to install Valgrind, and you can see that it picks up the dependencies from the /Spack directory. It picked up MPI over here and all the packages that it needed as dependencies like XZ or zlib. Valgrind is using it already from a Spack installation, which is in a read-only file system. It's downloading the source file, the source tarball of Valgrind, and it's building it. After it finishes this build, we will have Valgrind installed in a central directory in the home directory, which is then accessible to the compute nodes, and we'll be able to load it and use it. So here, it's doing the final installation, and it says it has installed it over here. I can look at this directory, ls, and there is a bin directory. It's installed. So I could just say Spack load Valgrind, and then Valgrind will be in my path. I say which Valgrind. There it is, Valgrind -- help. I put to more, and there it is. So all the libraries are loaded correctly, and it's installed. And it's installed in such a way that if I were to look at my host name and cat, say, etc hosts file, these are the two nodes, the nodes VM 0 and 1. I can SSH to them. And if I were to just do a Spack load there, Spack load Valgrind, even in the compute nodes, I can see that. Which Valgrind? So this just shows you that the set of packages that you can get in this E4S Pro image is not a static list. You can expand on that. You can deploy your Python-based tools for AI/ML. You can launch jobs on the compute nodes, and you can have the new tools that you install accessible. So this is a interesting cluster. Let me just look at running a simple MPI job on this. So if I say MPI proc name, and this is a MPI proc name.c file, and you can see I'm including the MPI.h for the message passing interface, which allows you to communicate between tasks. I initialize it, I finalize it, I can check the size of the ranks, the total size of the communicator and the rank, and each processor just gets its own name and prints out the hello world message. Now I can say compile.sh, and it's just a script that compiles the program .c into the MPI proc name executable. Compile.sh. And if I say cat run ODDC.sh, then here what I'm doing is I'm just getting the Nodus files from the etc hosts that we saw before and just printing the first column and putting it in a host.txt file. So I'll get 2 of these, and then I'm saying launch just 2 tasks, 1 processor per node, and here is the host file, the hosts.txt, and run this application. So I want to make sure that I can run this program on the compute nodes. See, I can easily say MPI run -np2 MPI proc name, and this is going to run it on the login node. There it is on E4S OCI, but I want to run it on these 2 nodes over here, these 2 nodes. So if I say run ODDC.sh, it will add it. And now I'm running on the 0 and 1 Nodus nodes. And so this is a simple example that shows you how to spawn these MPI tasks on 2 different nodes. What if you want to measure the performance of these applications? Here is a simple example, the molecular dynamics code called CoMD. And let me just go to the MPI directory here. I can say make clean. And then I can say make. And I'm building this code with the O3 optimization. You can see the O3 optimization level with the symbol information in there. And then let me just go to the bin directory. Let me say run oddc.sh. And here what I'm doing is I'm saying launch 4 MPI ranks, 2 on each node. Use this host file that we have just created in the etc hosts in my home directory, hosts.txt. It is hosts.txt. And then launch 4 processors along the X direction, 1 along the Y and Z, and give it some work. So it's running these on these 2 nodes. So I can say run oddc.sh. So you can see that it's doing this work. Now we want to measure the time it takes in different components of this application and say, find out where is it spending its time. So I'll use the tau performance system, the viewer for which we had just seen, the paraprof viewer, and we'll figure out how much time it takes in each code region in this application. Okay, so to run this same application with tau, I do not need to change the source code or the build system or even the binary. I can simply launch it. So if I say run oddc.sh, and this is the way I launch the CoMD MPI, then I can simply say run tau oddc.sh, where I'm using tau exec with the event-based sampling parameter and just launching the same exact application there. This is the only difference in these 2 files. And I can say run tau oddc.sh. It's launched on these 2 nodes. I can look at the execution, and it will run the application at roughly the same speed, and it will interrupt the program periodically. At each interrupt, it will translate the address of the program counter back to the source line location and tell you exactly what code region was responsible for the performance that you observe in the application. You can create profile files, you can create traces, there are viewers, but with ODDC, I can see the performance data right there without transferring it to my desktop. I can launch paraprof like this, and there are 4 MPI ranks here. And I can say right click here, show me the thread statistics table. Now it's showing me this table of what happened in this application. Let me just click it. In the tau application, it took about 35.4 seconds. You can open this, and it's saying that outside of these MPI calls, like MPI send, receive, all reduce, it spent about 34.8 seconds exclusively. And the event-based sampling can show me about 33.99 or 34 seconds out of the 34.8 seconds. And it can show you where it's spending its time. So with no change to the application, I could simply see that there is a function called LJ force. Out of the 33.9 seconds, 31.6 seconds are spent in this. If I expand this, I can see exactly what lines are spending how much time. So it says that forget about the rest of the code. You can see it takes very little time in functions like advanced velocity or sort atoms in cell. But in this LJ4, look at line number 198. It's spending 6.3 seconds in just this one line. I can say, show me the source code. It jumps to this. And here is the C code. And I can see that there are several loops here. So here is the function, is a for loop, 1, 2, 3, 4, 5 levels of for loops. And at this line, it collected as many as 211 samples and spent 6.3 seconds in this Leonard-Johnson force function in this molecular dynamics code. I can look at the breakdown across different functions. I can look at different ranks and how each rank was executing this particular line of code. And you get the idea. You can generate a profile file very easily and measure the performance of this code using tau. So with this, let me just go on to some other tools that are available. Now, we saw the visualization capabilities with Visit. We have another visualizer here called ParaView. ParaView from Kitware. You can launch ParaView with an output file. This file was created using a computational fluid dynamics code called NALU Wind from Sandia National Labs. And what it does is it has a visualization of this. Let me open this eye. And you can see over here, this is the surface with edges. And here is the turbulent viscosity. I can see a three-dimensional view of this plate over which a fluid flow was simulated. And if you want to see how the pressure was on this plate, here is the pressure. I can click the play button, and there you can see the pressure during the simulation. So this is just an example of the kinds of visualization that you can do with ParaView. And it's very responsive within this environment, and it's all running on Oracle Cloud Infrastructure on the head node. And you can run MPI applications on the compute node. You can generate the data. You can analyze them all through a remote desktop environment, which is a compelling way to interact with the cloud infrastructure. And there are some other examples that I can show you. For instance, let me just again launch ParaView and see some of the canned examples that come with the ParaView distribution. And here is some example visualizations. Here is a contour CT scan of a head. Here is a Exodus. And let me just show you this. Here is and I can look at this solid color for the surface point question. And look at another computational fluid dynamics code. Now you may see that when I say Spack FindX, there are many applications that are bundled along with this distribution. You can see deal2 finite element code. You can look at say OpenFOAM, and there is Quantum Espresso, and several codes like MFEM. Now, if we look at OpenFOAM, there is a cavity. There is run.sh, and then I'm just running this application. So it runs this, it's created the foam file, and it's launching ParaView again over here. And you can look at that. Apply surface with edges. I can see the edges. And you get the idea. You can analyze the results of this and see the output of the execution of OpenFOAM. OpenFOAM is a mature computational fluid dynamics code which is used widely in industry. And it's part of this distribution. If I go to Quantum Espresso, now here is a run file. Again, I'm using the host file to launch it on the compute nodes. And I'm saying run it on, say, 44 of these MPI ranks. Or maybe I should just change it to, say, 16. Run ODDC.sh. I'm doing a Spack load here. I'm going to go 16 and say launch 8 ranks per node. I can also specify the number of OpenMP threads and say, let's say two threads. I can say run oddc.sh, and this will run the Quantum Espresso code by doing a Spack load, and then you can see the results. Now, Quantum Espresso is a code where we can calculate the electronic structure of real materials and their physical properties by ab initio method in this Quantum Espresso. And you can see that this MPI application ran on the 2 nodes. Here is another code called LAMMPS. And in this run ODDC file, what I'm doing is, again, running, say, 2 OpenMP threads and running it on 32 MPI ranks, 16 per node, or maybe I should change that to, again, because our cluster has 16 and say 8. I'm loading this LMP binary after loading the Spack load LAMMPS. I can say Spack find LAMMPS, make sure that it's there, it's installed. You can see the version over here. And LAMMPS, or the large scale atomic molecular massively parallel simulator, is a classic molecular dynamics simulator, which also comes from Sandia National Labs. And here I'm running this oddc.sh, launching the MPI job, and there it ran on those 2 nodes with 2 OpenMP threads with 16 MPI tasks. So when you use a cluster, there are many concerns that users have. Is the performance of the MPI application going to be optimal? How do we ensure good intra-node communication? Now, intra-node communication is critical, and there are questions like, does this distribution have intra-node XP-mem? Does it have high bandwidth, low latency interconnects? Does it use the XP-mem, which is Linux cross memory attach? It is a kernel module that enables a process to map the memory of another process into its own virtual address space. And then you can see that these kernel modules are then used by the MPI infrastructure to ensure that there is good communication performance within the node, as well as externally. It uses the most optimal way to launch the MPI jobs across nodes. So let's take another example of, say, PETSc running on the CPU. So here is, let me say, clean.sh. This is an example from the PETSc solver. It's DMDI KSP solving a set of linear equations, Poisson equation in 2D. And you can see various header files and the PETSc calls for the API. I can say compile.sh, and it will use the Spack installed version of PETSc to compile this application. You can see the PETSc library as well as Hyper and SuperLU-dist, OpenBlast, a number of packages like Parmetis, Metis, and this gives you an idea of the complexity. Like if I were to say Spack find PETSc, it shows me that PETSc is installed. I can say Spack find PETSc with the dependency listing, with the variants, and you can see the PETSc, this is the hash, PETSc 320.1 is built on top of HDF5, which is, and it uses Hyper, Metis, MVAPICH 2, it uses Python, Parmetis, and a number of packages all installed using this extreme scale scientific software stack, or E4S. All of these packages are built with the same set of compilers and MPI. So they're easy to integrate into an application like this EX50 that I have just created. Now, if I run it on, say, 4 ranks, just 2 in each node, I can easily do that and launch it with run ODDC. There it ran on 4 MPI ranks. Now, I can also use tau again and say tau exec with EBS. Let me do something more interesting. Let me add some export tau call path equals 1, export tau call path depth equals, say, 100, and then export OpenMP num threads as, say, maybe 4. So I can say run tau oddc.sh. So it has got 4 threads per MPI rank. It's running 2 processes per node, and then it's launching the application, generating the performance data, and then we'll be able to see the full call path through this. So this is an example of it running on the compute nodes, and it's returning this. And you can see the profile files. If I launch paraprof, and I want to find out exactly where it is spending its time, these are the 3 threads, and here's the main thread. I can just click here, and it says it's spending 14.14 seconds in MATLU factor routine. If I open up the thread statistics table, let's open this up, and it shows you that it spent in main stage, PC setup, LU factor, and all the functions where it was called. And you can see the full details. Even inside an MPI application function, you can go inside it and see what it was doing. Like in this case, here is the MPIR reduce scatter block implementation, which comes from, say, this particular library of MVAPICH, which is called along this calling path of main stage, PC setup, MATLU factor, and this MPI I receive, where it spent that time. So you can measure the performance of your application. Here is the KSP solve routine. And let me just open up this PC apply, mat solve, and see the various components of this. And what is interesting here is that if I look at a collective operation, there is the MPI collective sync time. And the MPI collective sync time represents the time wasted in a barrier, an MPI barrier within a collective operation. So you can see exactly how much time it spent in this MPI all-to-all-V in a barrier call. So you can characterize the performance of your application, launch the visualization tools. You can see tools like Visit, TaraView. There are other examples here, say SuperLU-dist. Here is a PD drive.c, and you can see this code, SuperLU, from Berkeley lab, and say compile.sh. And it will use Spack to compile, to get the dependencies and build the code. And here is the run ODDC.sh, and it will run this application. And you can see how it's compiling the application using the Spack directory for SuperLU-dist. So with this, I should mention that not only can you use the packages that are installed here using Spack, you can see Spack find 124 now, because Visit, the Valgrind tool, has been installed here. But these 124 packages need many other dependencies. There are like 874 packages installed in this software stack, many Python packages, as you can see, and other HPC and AI tools, all within the same distribution, which makes it relatively easy for you to start using the resources provided by the Oracle Cloud Infrastructure. You can easily launch your cluster using the ODDC, and you can very easily look at the performance of your codes and measure their performance. You can even deploy other user-defined software stacks in this using other containers, because you can see that we have Singularity installed in this image, and it is a Singularity version 4.02. So you can deploy user-defined software stacks. You can bring in other containers. We have a large number of containers on the E4S page. You can go to the download section and download these Singularity files for different GPUs from Intel, AMD, and NVIDIA for different GPU architectures. You can use Docker, and these are the full-featured images. They are base images, minimal Spack images, and you can deploy them very easily using the Singularity containers and configure your cluster. Use the HPC Cloud On-Demand Data Center. You can go to the cluster, and you can even log in through this web interface, the dashboard, onto a system where you can say Nodus SSH, and then log into the compute node and say E4S. So you can then use the Nodus commands and say Nodus with the cluster, with the SSH key, even use admin to say E4S OCI. That's the name of the cluster that we just created over here, E4S OCI. So in the dashboard, I can say Nodus cluster SSH --admin E4S OCI, and then I can log in directly to that cluster. It expands the utilities. Who am I? And I can say sudo bash, and then you can see that in root, I will have the Spack, and I can have my set of tools. So I'm root over here, and I can log into the compute nodes and the login node in this way. So I have full control over all aspects of configuring and deploying a cluster on OCI using the ODDC interface. I do not need to install third-party tools. I do not need to install command line tools on my desktop to launch these clusters. I can connect to one or more cloud providers, choose their instances, compare their prices. I can see exactly how much each instance costs, configure my cluster, and use the credential manager to then authenticate and then launch a cluster, deploy it, and after I'm done, I can just destroy the cluster in this way. So all the aspects of the cluster management are then under the control of ODDC, from deploying to launching all the clusters. And you can easily switch between different instance types. You can configure your cluster and use this interface as the primary interface for interacting with the remote desktop environment, where all the tools are installed for your HPC and AI ML workloads. And you can use multiple nodes and use the E4S image. E4S is built on top of the Spack package manager, which comes from Lawrence Livermore National Labs, DOE. And you can use these images that are provided for different cloud providers. So you can reach out to us for customization of the image, what additional tools you may need with the base images that are provided, and be productive using Adaptive Computing's HPC Cloud On-Demand Data Center product. Thank you. And this brings down the cluster.